this Alessandro's?
Oops, I hope not.
I was not sure because I saw it only when it was too late. So.
No.
Or not? No, it's not. Okay, good. No, anyhow, somebody will find it.
There's a computer. So.
Okay.
Someone forgot this? Okay. There's a. I should say.
1,000 reals.
Okay, so let's start the fourth lecture of Marko on linear perturbation.
Okay, thank you. So, all right. So today we are going to discuss a bit more about these infrared contributions that we briefly talked about yesterday. Okay. So what we saw is that. So by the way, I like that there are many references that are kind of related to what I'm going to talk about, but most of the things that I'm going to talk about are in this paper. And also you can find the references inside if you're interested in more details. So this is maybe one starting point to look at, and then of course you can explore the literature further. So what we said yesterday is that, or actually even maybe the day before yesterday, is that these perturbation theory kernels have some particular structure when one of this momenta, for example, is soft or much smaller than the others, or you go to the infrared limit in terminology of quantum field theory. And this behavior was interesting because there was something that looked like a divergence. Okay, so you get 1 over Q in this limit. So these kind of contributions are much bigger than the other contributions in the perturbation theory kernels, which are of order 1. And then you may be worried that perturbation theory somehow it seems to be producing terms which are very sensitive to what happens on very large scales. But we saw in an explicit calculation that if you do, for example, one loop calculation, there are these kind of terms which appear in different diagrams, and they make contributions to different diagrams large. However, when you sum them up, they cancel among each other. So this cancellation of, sometimes people call this IR divergences, or maybe in this case, since there is no real divergence numerically, maybe you can call it IR enhancement. So the cancellation of these things we saw in the one-loop diagrams, but actually it happens more generally. It happens also in n-point correlation functions that happens at all loops, okay? So today, first, I want to say a few words about that. Why is this the case? Where does it come from? And then we are going to see that there is some extra expansion parameter in perturbation theory that we didn't notice before, and it is related to that. And then we are going to see how this extra thing is responsible also for the broadening of the BO peak, and we are also going to see how to take it into account, okay? Such as we're going to improve our modeling of the power spectrum. So the broadband is fine at the moment. However, we still had troubles with wiggles and the shape of the BO peak, and that looks bad. So we're going to see today how to make that work, okay? This is the plan. And hopefully everything will be done in 1 hour and a half, because we're anyhow a bit late. So first, let me say that there are, of course, we looked at the power spectrum. Let me show you one other observable, which is very important, which is the bispectrum, or the 3-point correlation function. I want to mention this for a couple of reasons. But let's just calculate it in the simplest approximation. There's a 3-level bispectrum. So when you have the nonlinear solution for the perturbation theory, you can calculate not only the 2-point function, but any n-point function. And in particular, let's see what is this: K1, delta K2, delta K3, okay? So this is a 3-point function. By translational invariance, it must be proportional to the delta function. So there is like 2 pi cube Dirac delta of K1 plus K2 plus K3. And then there is some function B of 3 momenta, K1, K2, K3. And we call this the bispectrum, okay? So what is the perturbative, what is the leading order perturbative solution for the bispectrum? If I use 3 linear fields, what do I get? 0. I get 0 because each linear field, of course, is just proportional to the linear field in the initial conditions multiplied by the growth factor. And if you have a Gaussian initial conditions, the bispectrum will be 0 if you put 3 linear fields. So what do I have to do in order to get a non-zero contribution? In the same way as for the power spectrum, I somehow have to have even number of initial fields. And the lowest order in perturbation theory when that happens, if I use like 2 linear fields and 1 second order field. Okay? So for instance, we can evaluate these 2 guys at linear level, and we can, for example, calculate delta 3 at second order. And at second order, it is the usual integral. There will be F2 kernel and 2 initial. Schematically, it's something like that. It's 2 initial fields. So you just plug here the second order solution. And then when you do the expectation value, you're going to correlate these 2 linear fields with these 2 linear fields here. And this is going to give you 2 possible contributions coming from 2 different contractions. And the final formula, for example, for this quantity at the 3 level, I'll explain what does it mean. So the 3 level bispectrum is going to be 2 times, because there are 2 contractions, F2 of K1, K2, P of K1, P of K2. These are linear power spectra. And plus, we have 2 other permutations. All right, so let me maybe explain a bit more the structure of this formula. So this F2 comes from the fact that you have 1 F2 in the second order solution. So when you do the contraction of, for example, K1 with this field, there is 1 delta function which tells you that the momentum must be opposite. And there is another delta function from K2 and this field. So basically, F2 depends on K1 and K2 then. And this is what is written there. And because you have 2 contractions, you get 2 linear power spectra, P of K1 and P of K2. Okay? Very good. But now there are 2 extra terms, because here we chose to put second order here, but we can also decide to put the second order here or the second order here. And these are these other permutations. So these other terms, this means like it has the same functional form. It's just K1, K3 or K2, K3 in these 2 extra terms, okay? So this is the meaning of these extra permutations. And in the terms of these like pictorial representations of these formulas, what we are doing is basically taking 1 second order field. So we have 2 initial fields which produce a second order field. And we are contracting it with 2 linear fields in the bispectrum. So we are doing this expectation value here, which means that we are averaging over these modes, gets 2 power spectra. And again, if I open up a bit, deform a bit this thing more abstractly, it looks like that. So there is some 3-point function. So here we have K3, K1, K2 as the vectors. And I have 2 power spectra, P of K1, P of K2. So you see that there are no loops here. There are no remaining momentum integrals. And this is why these kind of contributions are called tree-level contributions. These diagrams look like trees. They have just branches. They don't have any loops inside. So just the terminology. And for instance, these other 2 permutations are going to be the same kind of diagram. So K1, K2, K3. But when I put 1 power spectrum here and 1 power spectrum here, and finally, the last one will be K1, K2, K3, when I put 1 here and 1 here. But they have the same functional form. So these are 3 options. OK, so now the reason why I wanted to show you this is that just to see one other example of summary statistics, which is not just the power spectrum. If you want, for instance, you can start plugging higher order perturbation theory here, OK? So for example, you can do first order, second order, third order. It's 6 fields. And that will be like 1 loop bispectrum, okay? Or you can do second order, second order, second order. It's also 6 fields. It will also be 1 loop bispectrum, or 1, 1, 4, and so on. So there are many contributions here that you can write down. You just expand all of these fields perturbatively, take all diagrams or expectation values which have even number of fields, and you combine them, and you get similar expansions for the power spectrum. There will be a 3-level bispectrum here. There will be 1 loop bispectrum, and so on. 1 loop bispectrum will have loops, which will have integrals, where momenta run over high values of p's or k's, and then you will have to add also the counter terms. Here, for the bispectrum, the leading order counter term will not be enough. You will have to go to the second order counter terms as well in order to make sense of all these loops. But the story is really the same as for the power spectrum. But let us stay here at the 3-level bispectrum, because what I wanted to show you is that even in these more complicated statistics where you have more fields in the expectation value, the same cancellation happens. And here you may be worried, because if you look at this formula, you see that it depends on this kernel directly. So before, for the 1-loop power spectrum, kernels were inside the loops, and they had funny momentum structure, like p, k minus p, and so on and so forth. But here you really just get F2. And you may wonder, what happens when I take this B3 expression, and I send, for instance, K1 to be much smaller than K2 and K3. I can always do that. Why? Because I know that by this momentum conservation, these two momenta have to sum up to 0. And there is no problem in choosing one momentum to be very small, let's say K1, and then having K2 like that, and K3 like that. So this is a perfectly valid momentum configuration. I can look at this bispectrum when one of the Fourier modes has a very large wavelength or very small wave number, and the other two have high wavelengths. No problem. So what is going to happen here? You see, here you're going to get a contribution which looks like that. There will be 2 times K1 dot K2 divided by K1 squared, PK1 linear, P linear K2. So this infrared enhancement comes again. So you see, when K1 goes to 0, basically, this thing explodes. And that is a bit maybe worrisome or strange, that you're so sensitive to the infrared modes. However, the full answer, again, in the full answer, there is always a cancellation, because you have to remember that there are these extra diagrams. So there will be one more diagram, and in particular, it is this one. So here, you will have to add another piece which is very enhanced, which is 2 times K1 dot K3 divided by K1 squared times P of K1, P of K3. These are the only two which are enhanced. But now you see, at leading order, K3 is approximately equal to K2 in magnitude when you send K1 to 0. So P of K2 and P of K3 are almost the same. And there, these momenta must be opposite to each other. So this is why here K3 is approximately minus K2, right? And then these two expressions cancel at leading order. So these two cancel. So you can again see that in explicit calculation, there is this cancellation of these infrared contributions, okay? Not only in the loops, but also in any endpoint function. In fact, the statement is much more general. The statement is that if you have any endpoint function whatsoever, for example, delta of Q, and then delta of K1 to delta of Kn, you take like endpoint correlation function with density field fully nonlinearly, and even if these are galaxies now, so really completely non-perturbative, non-linear, most complicated possible correlation function, the general theorem is that in the limit, when Q is much smaller than any of these Ki momentum, what happens? This becomes something like this. So first of all, you may think that you're going to have some contributions of order k squared over q squared. You may think that you're going to have some contributions of the order k over q and some contributions of order 1 in this expansion parameter, multiplying p of q and then delta k1, delta kn. But however, the theorem says that these contributions cannot exist. So these are not there if f and L local is equal to 0. And these contributions cannot be there if the equivalence principle holds. So now these kind of contributions are exactly these ones. So you have a k over q in this more general example I call the soft momentum q. And those have to vanish always by the equivalence principle. Okay? So there are two assumptions in this theorem. One assumption is that you have a single field inflation. Single field inflation. And the other one is that you have equivalence principle. Now, this is a bit mysterious. Like, why inflation? Like, what this has to do with inflation? But I'll explain that, yes.
Sir, for example, for the cancellation, you use two diagrams, right?
Yes.
So there's the limit of the third one.
Oh, no, the third one does not contribute. And let us see why. Because the third diagram is this one. And this diagram is just F2, 2 times F2 of K2, K3, times P of K2, P of K3. And when K1 goes to 0, this doesn't produce any divergence.
So the formula for B, the first term does not depend on K3.
Sorry?
There's no K3 in this formula.
In this formula?
Yes, it's K1, K2, K3, K1, K3.
Yes, but then there are two permutations, and these are like the same functional form where you have K2, K3, and K1, K3.
Okay.
So this is what I was saying here, that you can put momenta in 3 different. So these 3 permutations, three possible terms just come from the fact that you can put second order solution here, in which case you have only K1, K2, or here. This is what it is. Yes? This one?
Yes.
That one comes from the following, that let us just focus on one term where we evaluate this field at second order. Okay? Then I have to calculate the expectation value of these 2 initial fields and these 2 initial fields. So there are 4 fields. There are 3 possible contractions. So I'm having 4 initial fields, and I can either contract this one with this one, or this one with this one, or this one with this one. There are 3 possible contractions that I have to do to get the full result. Now, if I do a contraction of these 2 fields, I'm going to get that the delta function tells me that K3 must be 0. And I'm looking at some 0 mode of the, which is not some background. We don't care about that. So there is no contribution to the real bispectrum. So the only 2 non-zero contractions are when I do K1 with the first thing or K1 with the second thing. But this one is symmetric in K1 and K2, and so this is why I get 2 times identical contribution, which is just this. So this factor of 2 comes from the fact that there are 2 non-zero contractions in the evaluation of this diagram. Yes? Yes, the second assumption is that the equivalence principle holds, meaning that all species feel gravity in the same way. Galaxies fall in the gravitational field in the same way as dark matter particles fall in the gravitational field. If that is violated, then there will be this divergence. And we are super late, anyhow. So that's too bad. It's very difficult to give lectures on the blackboard because with slides you can always speed up, but unfortunately when you get to write, I'm not sure about that.
As long as the equivalence principle is just that matter couples
well, what I mean here by the equivalence principle is really what Galileo meant by the equivalence principle. What this really means that if you were to produce a large homogeneous gravitational field with a uniform acceleration g, for instance, and you put a galaxy or a dark matter particle or like, I don't know, like a spaceship, they all fall with the same rate.
Okay.
This is what it means. Now, right, for the modified gravity, there are examples where this is not the case. So for instance, if you have some kind of a screening, then some type of galaxies will not fall in the same rate as the other type of galaxies. And in fact, in modified gravity, or if you put some fifth force for dark matter particles and so on and so forth, you're going to generate this term. And so one way of looking for any kind of strange modifications is exactly looking for this kind of term. Because remember, this equation is fully non-perturbative. This cancellation must happen like at all orders of perturbation theory, even beyond perturbation theory, non-perturbatively. So if you go and you measure your galaxy endpoint function and you find these kind of deviations, then you discovered new physics in the, we don't know what it is maybe, but it will be something that has to do with violation of the equivalence principle. Maybe not fundamentally, but in the effective way, that somehow because of the screening mechanism and so on, things do not fall with the same rate. All right, so let me sketch how to derive this formula. I will not do the derivation, but it is very easy, in fact. It might seem like it's non-perturbative, it's a very complicated, but in fact, given that it's non-perturbative, it means that there must be some simple trick to do it, otherwise you would never be able to figure it out, okay? So, the key to derive this is to realize what these terms actually correspond to. Okay? When I write something like that, what does it really mean? Okay? So let us take a look at that. Can you see if I write down here? It's okay? So remember that, so this piece, so the full F2 kernel has many pieces, and this is just one of them, very isolated piece, but we can say that second order solution, the full second order solution, has many pieces, okay, dots, but this one, remember, it is k1.k2 over k1 squared multiplying delta k1, delta k2, okay? So now this is written in momentum space, but what does it correspond to in real space? Maybe it's hard for you to guess immediately, but look, there is one k2 vector, and there is one k1 over k1 squared vector, okay? So remember, k1 over k1 squared comes from some sort of velocity, right? And this k2 is simply, can be seen as a derivative of this field in real space. So in other words, if I go to real space, this thing looks like that. So there is a gradient over Laplacian of delta times, well, gradient of delta. So you see, when I do the Fourier transform, this becomes vector k2, and this becomes vector k1 divided by k1 squared. And so when I multiply them, this is what I get. But now what is this? This I can write also as the gradient of the gravitational potential times derivative of delta. Okay? Because you remember, the gravitational potential, sorry, the delta is just the Laplacian of gravitational potential. So then the inverse Laplacian acting on delta basically is the same as the gravitational potential. And now, if you look at this term, you start to understand what actually it is, okay? So the gradient of the gravitational potential, what is this? The gradient of the gravitational potential is just the homogeneous gravitational field, right? So if this is non-zero, this means that you have some gravitational field, like that. So this is gradient of phi, okay? So if you have the Earth homogeneous gravitational field, it has a linear potential. When you take the gradient, you get G. So basically, what these terms are about is how the field delta changes in the presence of the homogeneous gravitational field. Okay, so basically this tells this kind of couplings, this kind of terms tells you what happens when you put density fluctuation in a homogeneous gravitational field. Okay. And so what happens when we put some density fluctuation in a homogeneous gravitational field? Imagine that we're always working in the limit. You should remember that we're working in the limit where this K1 must be much smaller than K2, which means that the wavelength of these Fourier modes must be much larger than this Fourier mode that we care about. So the typical situation is that you have a very long wavelength of gravitational potential, let's say. And if I specialize to some small region of the universe here, and I look what happens with the short wavelength fluctuations of delta. So what is the leading effect of this gravitational potential? So the homogeneous part, the constant part of gravitational potential doesn't do anything. In classical mechanics, you can always remove it. It's just an arbitrary zero mode, okay? But the constant gradient, so if you do some kind of a Taylor expansion of the gravitational potential around this point, the constant, so basically you can expand it in the constant piece plus gradient piece plus second order piece and so on. So this gradient, which is exactly this term, is doing something, okay? What does it do? It makes everything move with a uniform acceleration, okay? So everything just falls. So this is the effect of this long wavelength gravitational potential. And this effect is captured in the dynamical equations of motion, and it is exactly this kind of terms. Okay? So F2 kernel, F3 kernel, all perturbation theory kernels, they do have this kind of terms inside, and all these terms are related to the fact that in the long wavelength gravitational potential, things are in the free fall. Okay? But now, the free fall is something very simple. So for example, if you imagine that there is some galaxy formation happening in this region of space. So these density fluctuations collapse and form galaxies and so on. If there is no gravitational potential whatsoever, this long wavelength one, things will happen in some way, okay? Is that clear? I guess so. Now, if I put the homogeneous gravitational potential, how is this structural formation going to look like? Is it going to be different? Are you going to get different galaxies? Well, the answer is no. You don't get any difference. The only thing that is happening, so everything will be happening in the exactly same way here, except that now everything will be in the free fall. So this is the standard story of the Einstein elevator, right? No matter how complicated dynamics you have, if you put it in the homogeneous gravitational field, the dynamics doesn't change. It remains exactly the same. Everything happens in exactly the same way. The only thing that is happening is that everything is freely falling. All right, so this is the intuition between these kind of formulas, okay? Because this intuition allows us to say that the nonlinear field of galaxies, okay, in space, in the presence of the long wavelength density fluctuations, is the same as the nonlinear galaxy field. It will be exactly the same, but only in slightly different coordinates, okay? And here there is no long modes. Delta long equals 0. So there you can identify situation where you have nonlinear short-scale fields in the presence of the long mode with a situation where you have no long wavelength modes whatsoever, and all that you have to do is to go from one reference frame to another, just to go to a free-falling reference frame, and then everything looks like there are no long modes, okay? And this transformation from one coordinate to another is very simple, and it is given in the following way. So the new coordinates, tilde, are the old ones plus the growth factor. Well, let me just put everything together. So it will be like the gradient over Laplacian of delta. So this piece is exactly this piece, and it tells you by how much you move, okay? So you see, now there are two important points. This is an exact statement. If you just wait, depending on the age of the universe, this depends on time. There is a growth factor, so the longer universe evolves, the further away you go. You're in the free fall, okay? And this is the exact statement, okay? So if I have some delta, I want to replace, as you see, if I have delta galaxy field of X, I want to replace this with delta galaxy field of X plus gradient of delta. And this is the exact statement. But if I now expand in perturbations of delta, and this is what we were doing so far, we're doing perturbation theory. If I expand this is going to be delta galaxy of X plus, this is the leading term, and then the next to leading order term is just whatever is here times the gradient of delta G of X. And then there are many other terms. Okay? So you see this coupling here is precisely the coupling that was there in perturbation theory in F kernels. But it is there perturbatively, because we were always doing everything perturbatively. We were always expanding order by order in these fields delta. Okay? But these kind of arguments can be applied even non-perturbatively, even like keeping the full effect of these long Weber modes. So this is why this story of the free fall, which rigorously exactly this, turns out into some sort of couplings of this sort in perturbation theory. Okay? Is this clear? Am I going too slow or too fast? No reaction. Doesn't sound good. Rogerio is happy. I think that I'm like gauging my. All right. So now the point is that we realized that these kind of terms would produce large effects. They produce this infrared enhancement here. So you see there are big contributions. There were also big contributions in the loops. You remember, you calculate one diagram, you calculate another diagram. They're both large. And when you sum them up, they cancel with something small. So this somehow suggests that this thing, this delta x, that these displacements are large. They're not small. And in fact, we can calculate how large they are. So we can calculate, for example, some variance of this displacement field. Okay? How big are these things? And that is very easy to do. You just go to Fourier space, as always. So I have delta x times delta x. Delta x is this. So when I go to Fourier space, I will have d3k1. This is the usual story, okay? I'll do it once and then to remind you, but d3k2 over 2 pi cube. There is an expectation value of 2 deltas. So it will be delta k1, delta k2. This differential operator in momentum space becomes minus I k1 over k1 squared minus I k2 over k2 squared, because I have 2 fields, okay? And I have e to the, well, I k1 plus k2 times x. This comes about because I'm calculating everything in the same position in space. I'm just calculating what is the typical displacement produced by the long modes. And now it's all very easy, because this thing here is 2 pi cube Dirac delta of k1 plus k2. We already did all these things for the density field, but anyway, p linear of k. So when you get rid of one momentum integration using the Dirac delta function, what you end up with, this term goes away because k1 plus k2 is 0, and you're left with d3k over 2 pi cube, and then, well, p linear of k divided by k squared. Okay? So you see, this has a different form. So you remember that the variance sigma square of the density field was d3k over 2 pi cube p linear of k. So that was the variance of the density field, which was telling us how large are the fluctuations of density field in real space if you smooth them on a particular scale. Okay, so if you integrate to k max, which corresponds to roughly 1 over r, I'm going to get the variance of the density field. But here, if I want to calculate the variance of these displacements, I have a different formula, and it has powers of k in the denominator. And this means that the contribution to this integral comes mainly from smaller k's, okay, or more infrared modes. And this is precisely those kind of things that we see here. There is always one extra k in the denominator. And if you put numerical values, it turns out that this is roughly 10 megaparsecs squared, okay? So these displacements are pretty large. You can take a chunk of matter that is forming galaxies. If you put in the presence of the long wavelength mode, it will be now moved to another place, okay? So these large displacements or bulk flows, this is another name, maybe you heard about that. So these displacements or bulk flows are pretty large. They can change the density field significantly, okay? So it is a bit dangerous, in fact, in general, to treat them perturbatively, okay? They have a very simple effect, which can be treated exactly. If you treat them perturbatively, this may be a bit dangerous. We saw that there is always a cancellation, so we are safe, okay? But we're going to see also that the cancellation is not always really exact, and then something interesting happens. Yes?
That this estimate really has some range, okay? Like
Yes, but as I said, absolutely, I agree with you. As I said, for example, here, you're much more sensitive to the high k modes. But here, because you have 1 over k squared, for lambda CDM, you're not very sensitive to k max. Most of the contribution comes from large scales. And it is true. Here, I'm integrating to infinity. But even if I reduce this upper limit to whatever, k of 0.1 or something like that, this will be roughly of this size. OK. So now, so you see, this is the thing. There is some logic which tells you, oh, no matter how complicated things are, we know how to deal with these complications in this particular limit when I'm considering long modes and short modes. And then I know how to treat this effect of these long modes at leading order in gradients. I can treat them exactly, just a free fall. I don't have to treat them perturbatively. This is perturbative treatment. And because these displacements are large, they can produce large effects. Okay. Now they always cancel, and to see why they always cancel, we basically have to derive this equation. Now I don't have time to derive it, but I can sketch now where does it come from. So this was just a side to tell you like what really happens. We had to understand what is this, what does it really mean. But now it's very easy because the derivation. Can I erase these things? I guess that. Let me start here. The derivation is very simple. By the way, these formulas are sometimes called consistency relations. Okay, there are. For large-scale structure. And this is by analogy to consistency relations for inflation. I don't know if Merdad mentioned those. So he must have told you about the fact that in single field inflation, there is a famous Mosel-Sanders consistency relation which connects the 3-point function, the 2-point function. So this thing is a cousin of this inflationary one. So the logic behind it is exactly the same, and it's only applied to the large-scale structure. And there are also, for example, in gauge theories, there are soft theorems for photons and gravitons, which are also cousins of these things. Okay, they're derived in a different setup, but the logic behind it is always the same. Anyhow, it's just a side note for those of you who know what is it all about. So the derivation is as follows. What we want to do is to have n plus 1 point function on the left-hand side and some variation of the n point function on the right-hand side. And so we start usually in the following way. We say, like, oh, let me calculate what happens, even for galaxies, okay? If I start with an n-point function, and I ask what happens in the presence of some long wavelength mode, okay? I'm studying the n-point function of these galaxies in this region of space in the presence of the long wavelength modes. Well, we know what happens. This is exactly the same as the same n-point function. The statistics doesn't change. X1, Gxn, if there is no long mode. But now what I have to do is to change coordinates. I have to make everything go into the free-falling reference frame. Okay. And now there is some algebra here. What I can do to get the n, so the first step is multiply both sides by delta long, then average over delta long. On the right-hand side, when you do this, you're going to get n plus 1 point function. Here, when you do it, you can first expand this coordinate transformation because each delta x here is proportional to the long mode. And when you do this expansion, you're going to find that you have some term which does not depend on the delta long, which goes to 0 when you average over delta long. And then there is another one where you have linear in delta long when you multiply by delta long, and the average gives you 1 power spectrum. So the final result is something like this. If you go to momentum space at the end, I'm being a bit fast, but really, I mean, you can look in the papers to find this. I just want to show you the final result. The final result is something like this. Delta galaxy K1, delta galaxy Kn is, in the limit when Q is much smaller than K, becomes something like this, minus P of Q, and then there is some sum where A goes from 1 to n over all possible momentum. And you have things like K A dot Q over Q squared, and then times delta galaxy K1, delta galaxy Ka plus Q, delta galaxy of Kn. These primes mean that I subtract the trivial 2 pi cube times delta function. So this is only like whatever is remains when I remove the delta function. So I have n plus 1 point function on one side, and I have something which still has 1 over q terms times the n point function on the other side. And this equation just follows from this logic that all that I have to do, so there is no dynamics, there is no kernels, there is nothing. It's just change of coordinates and then doing some algebra. Okay? And now you can see the following thing, that here, if I assume that delta of Ka plus Q is approximately delta of Ka when Q goes to 0, then basically this can go outside the sum. I have sum over all Kas, and this just gives me basically almost 0, minus Q, if you want, by momentum conservation. And therefore, this enhancement goes away. Now, this is a momentum space formula, so maybe it's a bit difficult to understand really what is happening. But if you go back, I just wanted to write it down. If you go back here and take a look at this equation, all that we are doing, if you imagine that we are having some endpoint function that we are calculating in this region of space, and now we are saying, in the presence of the long mode, each field has to be translated, okay, by the free fall. Then, because we are applying the same translation to all points, all that we are doing is translating the whole region. And translations do not affect the correlation function. So this is why all these terms, because each one of these terms separately is a translation of individual field by the long mode. And if all of them are translated by the same amount, then the net effect of the translation goes away. Okay? So this is all that this is.
Sorry, can you repeat why when Q goes to 0, this thing goes out of the sum and infrared averages go away?
Well, naively, when Q goes to 0, actually when not even naively, but if Q is really, really, really small, then K plus Q is the same as K.
Yeah.
So this thing does not depend on Q anymore.
Right,
so it goes out.
Yes.
Okay? Also Q goes out. So you get sum over Ka. But sum over Ka is just basically 0 because by the delta function of the momentum conservation. Because again, all that this is a momentum space version of the statement take every single field, translate it in space, displace it by this amount, and this Ka comes from the translation, and then the net result will be 0. So now the important point is that, like, this is all fine. However, there are a few caveats here, okay? And let me say what they are. So the first thing is that we have to assume that in the first step, when we say that, oh, in the presence of the long mode, nothing is happening except that I'm going to the free-falling reference frame, this is not always true. So the long mode, we have to assume that delta long does not change initial conditions. So when we go back to this picture, and I was telling you, like, look, the constant gravitational potential doesn't do anything, and you were all saying, yes, we agree with that. This is true dynamically. So in terms of the equations of motion, dynamics, it cannot do anything. However, you remember that in the multi-field models of inflation, if you have local non-Gaussianities, then the constant gravitational potential, which is basically the same as constant zeta, can affect initial conditions. If you have higher or lower value of the gravitational potential, you're going to have a higher or lower value of density fluctuations or like variance of the density field in this region of space. Okay, so you see, the requirement that here everything is the same with and without long mode also means that the long mode doesn't change initial conditions. And that is true only in single field modes of inflation, where there is no local non-Gaussianity. If you have local non-Gaussianities, this is the same as a statement that the gravitational potential can change the variance of the density field on some scale. So this actually means that FNL local must be 0. So only then this statement will be exactly true. Okay? The second statement was that everybody falls with the same rate or by the same amount. So in the homogeneous gravitational field, everybody is displaced equally. Okay? And here is the point where the equivalence principle comes in. So if there is no equivalence principle, then when I put, for example, different galaxies, one of them is large, one of them is small, the other one is red, one of them is blue, they're all going to fall by slightly different amounts, and I'm going to displace them by slightly different amounts, and this cancellation then will not happen. I will have some net residual 1 over q thing, okay? So it is crucial to have equivalence principle. And the third assumption is that delta of k plus q is approximately delta of k. That was one of the assumptions to say that nothing will happen, okay? Yes? Yes. Yes, we cannot derive anything in this case. We cannot derive, but what we can say is that there will be some term, for example, if there is local non-Gaussianity, there will be some term of this sort. And in fact, the scale-dependent bias in local non-Gaussianity, if you heard about it, exactly looks like that, 1 over q squared. And this is the consequence of this. And also if you look, for example, in the bispectrum, inflationary bispectrum, if you have a local type non-Gaussianities, it will produce this kind of terms in the 3-point function for galaxies. And this is very nice because you see, no astrophysics, no matter what happens with galaxy formation, feedback, baryons, whatever, they can never produce these terms as long as they obey the equivalence principle. So if you find these kind of terms in your galaxy survey, it must be only local non-Gaussianities and nothing else. So this is why this is so powerful. It's a non-perturbative statement. It means that go to whatever high K modes you want. Don't worry about nonlinear effects. Don't worry about feedback. Don't worry about anything. The statement is that if you measure the 3-point function all the way to the nonlinear regime, and you see that there is some K square over Q square term, it must be only due to non-Gaussianities and nothing else. Or systematics, usually, in the telescope in long modes, but that's another story. In ideal world, it must be only non-Gaussianities.
There's no consistency relation
No, there is no consistency relation because then we cannot do even the first step. I cannot write this down and I don't know how to proceed, but I know that no matter, I cannot calculate the details, but I know that there will be this kind of term there. Okay. The same is true if you have single field inflation, but somehow your modified gravity or some other miraculous thing, like changes this effect of the equivalence principle, then you're going to find a second kind of terms. So that would be the sign of modified gravity. And if none of them is there, then everything will be fine, and we cannot say much. Now, people check these consistency relations. There was a recent paper.
Did you see that one goes up with k square over q square, and the other
Yes.
is like linear?
The reason why they go like that is because the non-Gaussianity part is sensitive to phi. So when you turn it to delta, there is 1 over k squared, okay? While the equivalence principle, whether you're displaced by the same amount or not, is sensitive to gradient phi. So when you turn to delta, you have only 1 over q. And this PCZ is the equivalence principle because it has to do with the translation. Sorry, this is a bit fast, I understand, but I think it's better to see than to go into the details.
So you're mentioning a lot this local type of non-Gaussianity.
Yes.
What if you have a general type of non-Gaussianity?
If you have general type of non-Gaussianities, this is perfectly fine. So the real statement here is single field inflation, really, rigorously speaking. So you want to have a single field inflation. If you have a single field inflation, there is no problem to have equilateral non-Gaussianities, but they will not change the fact that this is still true because in the equilateral non-Gaussianities, if you go to a squeeze limit, you have k squared times phi. So basically, you have a delta. So these kind of terms produce this thing. There is no issue with that. You can have general non-Gaussianities. The real statement here is like single field inflation. Yes. Well, not a problem. I mean, you may think of it as a great opportunity because you can just go to nonlinear scales and. So people check these things in the simulations, and in fact, they do work. There was a recent nice paper where people also use them to do some more complicated things, but I'm not going to talk about that. This was just to mention that there are these kind of non-perturbative results, and they're related to our story of today, of these IR contributions. We can treat these IR contributions without expanding things in perturbation theory. So in some sense, if you think about this from the perturbation theory point of view, it is the same as taking all possible FM kernels and picking up every single contribution which goes like 1 over qi over q squared, and putting it together, or exponentiating it, or resumming it, okay? But this resummation is here very simple. It only means that you do the full displacement rather than expanding it perturbatively. This is all that it is. All right, so now, for the rest of today, I want to talk about this third assumption, which is the most tricky one, in fact. Rogerio doesn't like.
Really? When q goes to 0, does not obvious?
Not really, yeah. This is why these things are very curious, yeah? So let me explain in what sense this is not true. I mean, of course that when q goes to 0, strictly speaking, this is true. But we don't live in the world where we are allowed to send q exactly to 0. I mean, the question is always about small but finite quantities. Huh? So what about this story? Yeah? So do you know why this fails? I already told you yesterday, but let's see if you paid attention. Zero attention, probably. Well, the reason why this fails is the following: that I told you the first day. It was not just to remind you, but there is a very important fact about our universe that there are many, like, for example, in the power spectrum of these density fluctuations, which is initially from inflation scale invariant. It's a very simple thing. It doesn't have any scale in it. There is no feature in it. The late time evolution, like recombination, baryonic physics, like transition from radiation to matter equality and so on, those processes imprint a lot of scales. So when you look at the final linear power spectrum, it is something like that. It looks like a scale invariant particle from inflation on large scales, then there is a quality scale, then there's some BO wiggles, there's this suppression, we have to calculate from the transfer function, and so on and so forth. And so then, it is not enough to say like, oh, this q just goes to 0 and this is true. You have to be worried about the presence of these other scales in the problem. Okay? And let me in particular say that obviously you can be in a situation where q is much smaller than k. But for instance, q happens to be of this size, and k is somewhere here. So k is much larger than q. But q is still comparable or larger than some frequency of the BAO wiggles. So there is some scale here, which is k BAO, which tells you what is the frequency of the BAO oscillations in Fourier space. And if your q is comparable to this scale, you cannot do this approximation because there is no Taylor expansion now. You're trying to do a Taylor expansion of a sign, but you have some finite q and you cannot do anything. So you see, this thing is not true in the universe which has features. This statement is always true only in the universe which has a very smooth power spectrum or very smooth correlation function. Only then this step is always possible. And only then you don't have to worry about all these infrared enhancement because by this theorem you know they will always cancel. There will be nothing to see. No matter what you calculate, at the end of the day they will cancel, they will go away. But only if your power spectrum is featureless, only if your correlation function is featureless. But in our universe we do have features, and that's beautiful because then these features can show us that these infrared contributions are important because there will be this step where this is not possible, and therefore this cancellation will not happen, and there will be some enhancement, and we can do something interesting with that. Okay, so let's see what can we do with that. So is this clear? Yeah. So now, so what is this feature? Let us go now back to real space, because maybe it's a bit easier. I mean, here with these things, it's sometimes easier to think in real space, because you have some mental image that these long wavelength modes are just moving things apart. So here, it was crucial when we were deriving these equations. We were saying, oh, but whatever endpoint function is here, if I just translate everything, because I'm in the free fall, everything will remain the same, assuming equivalence principle and single field inflation. So where is this issue in this real space picture? How do I see that I'm in trouble if I have features, if I go to real space? I don't see any problem here, okay? So let's see where is the trouble, okay? So in real space, the equivalent of the power spectrum is the two-point correlation function. And if I do the Fourier transform of this curve, I'm going to get something like that. And then here is roughly 100 megaparsecs. This is the BO peak. Okay. So you see, I have some sharp feature, which essentially means that if I have a galaxy here, there is some enhancement in the probability to find another galaxy at the distance of the BAO, roughly this 100 megaparsec. Okay. And this feature is very sharp. So the distance from the origin is like, I don't know, roughly 100 megaparsec, but the width of this is roughly 10. So therefore, I have some sharp feature, if I think about it mentally, some kind of sphere or a ring in real space. There is no such thing, of course, because you do the full statistics and you find this enhancement. But just for the purpose of illustration, let us think in this way. And there are two scales. There is this scale here, which I will call sigma, which is the width of the BAO feature. And there is this scale here, which has to do with LBAO. It's the BAO scale. Now, let us see how this story of moving things around apply in this situation. So here, I never had any feature. I was just assuming that everything is very smooth and homogeneous. So everything was moving back and forth, and there was no issue. But now, what happens if I go here and I start moving things around? Okay. So first of all, option A. So now you see the problem is that we have two scales. So there is if you think about some scale of momenta, there is okay, let me put it here. There is LBAO to the -1. Then somewhere here, there is sigma to the -1. They're well separated. And we can choose these long wavelength modes to be anywhere in between. So first option, let us choose Q, the typical wavelength of these long wavelength fluctuations, to be much smaller than LBAO to the -1. Okay? So I'm considering a very long wavelength mode whose wavelength is much bigger than this ring. What is going to be their effect? Their effect is going to be that they take this ring and just coherently move the whole thing in some direction because of these large bulk flows, okay? And then the picture is exactly the same as here. So nothing changes, right? And so therefore, there is no issue here, no problem. The consistency relations hold in the exact same way as before. Nothing happened. Option B. Of course, if I take Q to be bigger or comparable to sigma to the -1, then again there is no problem. Because I'm talking about some very small wavelength fluctuations. There is nothing interesting happening here. There are no features on higher scales, so everything is still fine. I can look at the dynamics on small scales. These are all some kind of UV contributions. I don't really care about this example. And there is option C, which is the most interesting one, is what happens when LBAO to the -1 is a bit smaller or comparable to Q, and this is still larger than, sorry, this is still smaller than sigma to the -1. What happens in this case? Do you see what happens? No, everybody's sleeping. I thought that having a lecture at 11 is much better. It doesn't seem to be the case. Too bad. I should try after lunch. So what happens in this case is that we have the long wavelength fluctuations, but now you see the wavelength is not much larger than the size of this BA ring, but you have some long wavelength fluctuation which look like that. So true, they are long wavelength compared to these objects here. And so for each bunch of galaxies here, I can say, oh, they're just going to move in the free fall because the long wavelength mode is like such, and it's much bigger than sigma and so to the -1 and so on. But the problem is that now there will be no coherent motion on the BAO scale, because here it will move in a different direction, and here this one will move in a different direction, and here this one will move in a different direction. So if you consider the wavelengths in this regime, it is still true that I can describe the dynamics of the interaction between the long wavelengths in this region of space only through these bulk flows. But now the thing is that these bulk flows are going to produce some observable effect. There will be no cancellation because they take my sharp feature and they move things randomly in the random direction. And so as a consequence, after the nonlinear evolution, so again, if I have some BAO scale, now this feature will be much broader. Because even if ideally I had a delta function before, that things move around, and when I average, I have something which is spread out. Okay? So this is your observable effect of these long wavelength modes. And in terms of the formula, what really breaks down is exactly this. I cannot replace delta of k plus q with just delta of k because there are some oscillations here. And this kBAO is exactly 1 over LBAO. So in fact, when I have, right? So when I have wavelengths here of the size of the LBAO, I cannot simply say everything will cancel here. So something will survive. Okay? And so it is this thing that leads to the broadening of the BAO peak. Okay? And now, coming back to our perturbation theory, I told you we were treating these displacements perturbatively. So we had some perturbative description of the broadening of the BAO peak, but it looked like nothing. It was a complete disaster. Why? Because these effects are large, as I told you, and we were just expanding them. So to get something reasonable, we have to keep their effect not expand it. We have to keep it resound. Okay. So let me remind you.
Why don't you have a displacement of the BO scale? Because you have a difference potential in the middle of your.
Sorry?
Why don't you have
the shift of the BO scale? Right. So because on average these things cancel, they move things closer and further, closer and further. So you just, on average, stay with the same size of the BO ring. But it's not entirely true. In fact, there is some shift of the BO scale because of the nonlinear evolution. But that one comes from the wavelengths, which are roughly of the same size as the BO scale. And then it's a bit like living in a curved universe. Okay. So there are parts of where there's a bit of more of a curvature, a bit less of a curvature. But that, when you average, the net effect is not zero. It pushes the BO peak in one direction or the other. But just these simple shifts, they don't change the position of the BO peak. They change only the width. They make it broader. But the true dynamical effects also include real dynamical effects of these long modes, which can then shift the position of the BO peak by 1% or so. But it's not much, it's calculable, but it's real. OK, so this doesn't work now. This is too bad. Yeah, it was working, but it doesn't matter. I mean, maybe. Sorry about this. OK, sorry. Yes, I had to go out from the full screen mode. It's always some complication. All right, so first of all, this is the illustration of what I was telling you about. It's just a cartoon. I already explained at the Blackboard. There is no point to explain again. But you see, yesterday I was telling you that if you compare to simulation, and again, this is 1%, so it's a very good simulations. And like if you look at the, roughly speaking, one loop perturbation theory is not so bad. It is wrong by a few %. So you might seem this is very good. Well, however, when you take a look at the BO peak, it doesn't look like anything. Okay. So something which is supposed to be a broader linear BO peak becomes something which has all these complicated wiggles. Why? Well, because we were treating these displacements only perturbatively. Okay. If we were to take them into account non-perturbatively in this sense, then things should look much better. And we understand this from this intuitive picture. Okay. And in fact, this is going to happen. So once you include this thing in the formula, you're going to get a much nicer, smooth power spectrum. So there are no residual wiggles when we compare to the nonlinear theory from simulations. And this means that the BO peak must be right. And in fact, it will be right. And this is what we're going to get, something very nice. Okay. So now I want to explain what are these different curves on this plot. And this is the last 20-minute discussion. Sorry, Roger, can I turn on the lights? Yeah.
Good for me.
I'm not sure, but all right. So let us see how do we get to these equations? What goes in this calculation? Again, it will be just a sketch. You can take a look at papers for more details. But intuition is what I explained. So now the only point is that we have to put this intuition into formulas. And that's not very difficult because, again, there is no dynamics here. It's only moving particles around. And that's very simple to explain, to describe with equations. So is this super boring for everybody? I mean, like, are you excited about this? Like, look, we can describe the BO peak, or not, or whatever. Or just fit with some Gaussian. It's as good as.
You will not say anything about the curves, right?
No.
The Simonović, right there is like perturbation theory, which Simonović or is just
Yes, this is just the Zeldovich perturbation theory.
Okay. So it's very close to the one.
Yes. I'll comment on that. Yeah. Okay, so now, yes.
So in that picture, actually what happens is that you may have a broadening that is not symmetric with respect to.
If you have a single Fourier mode, yes, it would be some anisotropic broadening. But when you average over all possible realizations of the long modes, on average, because you're always averaging over the sky, it will be symmetric. Symmetric in all directions. This is what isotropic maybe it's fair to say. Okay, so the logic to derive an improved, so remember before our model for P nonlinear of K was that we had P linear of K plus P1 loop plus P counter terms. So, and that didn't work quite well because in all these calculations, we were always treating all these displacements perturbatively. So now let us do a bit better. Let us see how can we do a bit better. So what we essentially want to calculate, imagine that you have some position in space, which is the origin. And let me, for simplicity, choose things such that I have one point here, another point here. This is x half. This is minus x half. I can always do that. I can always translate things as alike. So I'm considering some delta galaxy at x half and delta galaxy minus x half. So if I ask myself, what is the 2-point function delta galaxy of x half and delta galaxy of minus x half, which essentially is by definition psi galaxy of x. Okay. And so let me now call this some psi galaxy tilde, which is in the presence of the long modes. Because this is what we are calculating. We are calculating what happens with the pairs of galaxies in the 2-point function when I put these long wavelength fluctuations. This is what we want to do.
Sorry, the displacement is close with the bulk flow.
Yes, this is the bulk flow.
And long wavelength mode is what is causing.
Yes, yes. There are the long wavelength fluctuations. There is some long wavelength gravitational potential. This is causing these bulk flows. When you look at the M-body simulation, things move around. So this motion is what we are capturing here. Yeah, exactly. So now, here, we know what this is. All that we have to do is to basically do some translation here and some translation here, okay? So if you go to Fourier space, okay, what does that mean? It means that I can write this down as some integral of d3k. Again, I'm doing Fourier transform of this field, of this field. We did this very many times. So let me do it again. And then never again, I guess. 2 pi cube. Here we have delta galaxy K1, delta galaxy K2. And then, what do we have? We have factors of IK1 x half. We have a factor of IK2 minus x half. This is just Fourier transform. And now, each of these positions is displaced by some amount. This is the effect of the long wavelength modes. So here, I have x half plus delta x1. So let me write it like that. IK1 delta x1. And then I have the displacement here, which is plus IK2, or actually minus, because it comes with the opposite sign, delta x2. Okay? So now I get, so this is what happens. Like there is some bulk flow here, so there's some delta x, I call this the delta x2. There is some random delta x1 here. And now we are wondering, what is the effect on the 2-point function when I do this? I have some long wavelength modes, and this is the effect. But on top of that, what I want to do is to average over all possible realizations of the long modes. I want to smooth if I put a single long wavelength mode, this is the effect. And then, of course, it will be anisotropic. But if I smooth over all possible long wavelengths, configurations, and so on, then I have to calculate the expectation value. And this expectation value over the long modes acts only on this displacement. So there will be some expectation value here of the long modes. Okay? And now the rest is just some simple algebra. So you can express, you remember that each of these delta x things was just a gradient of a Laplacian of delta along, okay? So you have to plug this thing here, calculate this expectation value, and so on and so forth. So this expectation value is very simple because exponent is proportional to the long wavelength modes, which we can consider to be linear modes. And so for example, you can use the fact that e to the ix, if x is a Gaussian variable, becomes e to the minus 1/2 x squared. So this is true if x is a Gaussian variable. So you can come here, replace this expectation value with the expectation value in the exponent, and keep doing the calculations. Okay. Let me do one more step just to simplify it to a form that is maybe easier to see. So here, of course, there is a 2 pi cube delta k1 plus k2 and so on as usual. That cancels one with integrations. So we are left with d3k over 2 pi cube. There is a p galaxy of k e to the ikx, as you would expect in the usual Fourier transform. However, because we have long modes here, there is an extra piece. And this extra piece is nothing but, let me put it like that. It's exponent. So this becomes minus 1/2. So look, here, K2 is...
Why delta x1 has different signs from delta x2?
I think because there is this different sign here. I'm just defining, well,
Defining that, okay.
maybe it's the same. I'm not sure. Plus or minus. If you're a bit careful, you can figure it out. Yeah.
So just to make it clear, are you considering small perturbations on this new mean value? You're taking this in L?
Yes, I'm considering what happens in this situation. It's literally this. I want like just to see how the 2-point function looks like when I put some realization of the long wavelength modes and I average over all possible long wavelength modes. If I put a single realization, I displace these two particles in one way. But now I want to see if I average, if I put all possible configuration, what happens. So you see, to derive the consistency relations, we use a slightly different procedure. There, we would like to go to the m plus 1 point function. It was a bit different here. I don't want to calculate m plus 1 point function. I just want to see what is the reaction, what happens to the 2-point function when I add long wavelength modes and average over all possible realizations. And what enters here then, because here K2 is just minus K1 and so on and so forth, you have Ki, Kj, and then here you have expectation value of delta x1 minus delta x2, I, and the same thing delta x1 minus delta x2, j, okay? So what is this? This is the relative displacement between these two galaxies. So the relative displacement tells you by how much this distance changes. And you're calculating the expectation value or the variance here of this relative displacement in some sense, okay? And so on average, you're going to correct your correlation function by something which depends on the variance of these displacements, okay? All right, so so the final formula, when you calculate this expectation value, which is not much more difficult than what I did at the beginning, okay? When I calculate just the variance of a displacement at a single point, when you do this pairwise, like variance or the relative displacement variance, is the same steps. You go to Fourier space, there will be a delta function, so on and so forth. And what you end up with is that the galaxy correlation function in the presence of the long modes of x is something like this, approximately, because there are some approximations. If you look in the paper, is d3k over 2 pi cube. So of course, there will be e to the I k x. There will be e to the minus sigma square of epsilon k times k squared. And there will be the power spectrum, the wiggly power spectrum, well, galaxy wiggly power spectrum of K. Now let me explain what these things are. So first of all, this quantity, sigma square, is just 1 over 6 pi squared integral up to lambda of dq, p linear of q, and then 1 minus j naught q LBAO plus 2 j2 q LBAO. Now this looks like where does this come from? But it comes from these factors. I'll explain. There are a few comments I want to make. So all these factors come just from doing these different contractions here, and they involve sine and cosine of q dot x and so on, things like that. And because of isotropy, you just get k squared here at the leading order. And this k squared is the same k squared here. Okay. Now, what are the comments that I want to make? So the first comment is that act only on p wiggle. Why do we want to act only on p wiggle? Well, because as explained, if you have any kind of featureless power spectrum or correlation function, the effect must cancel exactly. So these kind of things should act only on the wiggly part of the power spectrum or the BO feature in the correlation function for the reasons that we explained here. Okay. So this is why here what appears is LBAO, because in this formula I'm saying that x is approximately equal to LBAO. I'm interested in what happens around the BAO scale, okay? Not anywhere for the correlation function, because in the broadband part, which is smooth, there are no these effects. They exactly cancel.
Sorry, that's too fast. So what is this subindex epsilon k?
This is the second comment. Yeah. No, you are too fast. You see, this is the. Now, this thing here is to remind you that when we include, so you see here we're including some long wavelength Fourier modes. And when I go to Fourier space, I will have some integral d3q over 2 pi cube, delta of q, and so on. But I don't want to include all possible long wavelength modes. I have to cut them off, because I want to consider only the long wavelength modes compared to this sigma. I don't want all possible Fourier modes. And more properly, so I want to include in sigma squared only q smaller than some epsilon k. So if I'm considering a k wave number that contributes to the correlation function, I don't want to include long wavelength modes which are shorter than k. This doesn't make any sense. This argument that we use to derive this formula of bulk flows applies only if I'm talking about the long wavelength fluctuations, not the short wavelength fluctuations. So for each Fourier mode k and this contribution to the correlation function, it makes sense to talk about bulk flows that come only from larger wavelengths or smaller q's. And this epsilon is some number, small number. It's like a parameter. I don't know. You can choose it as you like in practice. But even if I set epsilon to 1, it's probably okay. So this epsilon is a number less than 1, but even 1 is fine. Okay. So I can just say, like, let me take q always less than k. So when I'm calculating this variance of this relative displacement here, I'm going to get exactly this formula. So this is what it is. And in this formula, given some k mode here, I don't want to include all possible Fourier modes. I want to include only those Fourier modes for which the argument applies to begin with. Okay? So this is why, given some k which contributes to the correlation function, first, I act only on the wiggles because it's all about features. And second, I keep in these relative displacements only long wavelength Fourier modes compared to a given k. So this is why here, instead of generic lambda, I have some epsilon k. I have to cut off this integral. I don't want long modes which are shorter than the...
Is this integral finite if you take lambda to infinity?
Absolutely.
So the long wave modes probably don't
Exactly. So that is a third thing.
Oh.
So now many people use this formula. So in the literature, there is a formula where you use epsilon square infinity. So you just forget about this argument and say, like, let me put infinity here and integrate over all possible Fourier modes. You get a finite answer. But there is a difference between doing this. It's still not, it's a non-negligible difference. It's maybe 20, 30% different answer.
That's an exponent.
And it's in the exponent. And so the question is, like, how can you trust this formula? How do you know that this 30% that you're including makes any sense? Because this formula is derived using this bulk flow argument. So why now I'm allowed to include those Fourier modes which are shorter than my k mode that I'm looking at? And then it happens that this works beautifully. But it's a pure coincidence of lambda CDM. For instance, if you take the linear power spectrum, and you just imagine that there is another bump here, for instance, on small scales, there is some extra power because some glitch of inflationary model and so on. And you calculate this integral to infinity, a disaster. It's only in lambda CDM that miraculously it happens to give you the correct broadening of the BOP. But morally correct formula, the one that you can defend on the court, is the one where you stop at some point. For each k, you're considering only the Fourier modes which are longer, and that you can defend. Okay? And in fact, in this plot, what is shown is what happens when so now you can do various improvements of this formula, okay, in perturbation theory. I don't have time to discuss all that, but it's to give you a flavor. So what goes into this derivation? This is the basic result, I would say, okay? And in fact, if you just look now into these curves, so the linear theory is the black curve. I can do it, don't worry.
It's the first one on the left.
Good. So, so this, the black curve is the linear theory. The data points are some very high advanced large volume simulations. So you have very tiny error bars. And now, if you apply this formula that derived here, acting only on the wiggle part of the linear power spectrum, you get the blue curve. So you see, there is some broadening, but it is not enough. Why is it not enough? Well, it is not enough because we didn't integrate to infinity. Miraculously, if you integrate to infinity and just plug this number, whatever comes out, 36 or whatever is the variance of the displacement field, you're going to get something much closer to the data points. Okay? This is an accident in lambda CDM. So you can do it because phenomenologically you will be fine, but it is better to know what is happening. I think it is better to understand that you're not really supposed to do it and find some other way around this issue, okay? But if you just blindly apply this formula, if you take, for instance, if you say like, oh, my nonlinear power spectrum, forget about loops or anything, it's just the linear power spectrum, which is just the non-wiggle, smooth linear part of the power spectrum, plus this thing acting on the wiggly part, and it's calculated using this formula, then you're going to get a blue dashed curve. So it doesn't look great, but it is already some improvement. And as you can see, like the BO peak position didn't change very much, even though in the real data it is shifted because of the effects that I described before. So the true dynamics also includes a bit of a distortion of this ring because it lives in the overdense or underdense universe, which net effect is not zero. But here, these shifts do not do much. So how do we improve the situation? Well, one way, integrate to infinity, but it's not a satisfactory way. The other way to improve it is to realize that this thing, if I just use the linear theory and these shifts, is only the leading term. I can do better. I can start with my perturbation theory formula. I can split this into wiggle, non-wiggle parts, and I can try to correct both wiggle parts here and here by this displacement amount. Okay? And so if I do that, if I do a bit more sophisticated formula, being careful not to do double counting of these shifts and so on, then I come to this purple dot dashed curve. And then everything makes sense. So the very naive guess with only linear theory doesn't really work, and it is not supposed to work because we know that there are extra true dynamical effects that I have to take into account. It's not only because if the blue formula works immediately, there is something terribly wrong, actually. How come that you take, like, perturbation theory kernel, you isolate only one piece, and this gives you the full answer? This cannot be true. So sure, it is a very important piece because it leads to the proper broadening of the peak. It doesn't produce these funny wiggles in the peak, but it cannot be the whole story. There are other dynamical effects which are as important at some level. And so there is a way to systematically include order by order in perturbation theory all dynamical effects and always keep resummed all these contributions completely, okay? And this is what is called this IRS summation, right? And this is how does it look like at the one loop level. And if you add two loops, it will be even better. It comes even closer to the points. So this is just to tell you that there is a way in perturbation theory to do everything perturbatively as we did the first 3 days, but also keep into account these bulk flows. And now everything makes sense. So you use this formula, which you can defend, and you can say, okay, I believe this formula. And second, you know how to improve it. You know exactly what to do. Just do higher orders in perturbation theory, include more dynamical terms, which bring you to the correct shape of the BO peak, the correct position of the BO peak, and so on. And at the same time, keep systematically everything resummed, what you can resum. Okay? So this is what goes into this formula. Now coming back to your question about Zeldovich, so what is shown here is the Zeldovich approximation for the shape of the power spectrum, or sorry, the BO peak. Now Zeldovich approximation is another way of doing perturbation theory that I didn't talk about because I didn't have time. It is, you may know it as a Lagrangian perturbation theory. So in Lagrangian perturbation theory, the fundamental objects are not densities, but displacement fields. And so there you can calculate, for instance, perturbatively how much you're displaced from the initial Lagrangian coordinates to the final Eulerian coordinates. This is your variable. And you can do order by order perturbation theory in this variable. Formally, these two perturbation theories are identical. So if you expand one, you get the other. Or you resum one, you get the other. So they only have slightly different perturbative expansion. Okay? So because Lagrangian perturbation theory takes into account all these displacements, not this one that we talk about here, which are always in the finite Eulerian space, but displacement from Lagrangian to Eulerian space, it also captures parts of these kernels that are relevant. And so it automatically resums all these infrared contributions. And this is why Zeldovich approximation is a very good approximation to the shape of the BO peak, automatically. The problem with LPT, and the reason why I didn't talk about it that much, is that it is always very difficult to calculate things in LPT. It's a bit more difficult to calculate, for example, the correlation function of density field than in Eulerian perturbation theory. And given that we do have a way to resum these important terms in the Eulerian perturbation theory, practically this one is much easier to deal with. But these two things are equivalent. Also there, you will get the counter terms. They're the same counter terms as here. You can do like endpoint functions. You can do whatever you want. But you just if you want a filter definition, which has slightly different expansion parameters. Okay? Now, one thing to note is that Zeldovich broadens the BO peak a bit too much. So you see? Like here, this orange line goes a bit above the points. Here goes a bit below the points. And the thing is that once you broaden the peak too much, you cannot undo it. Like, no matter what you do, you always broaden it always more. So this means that if you include higher orders in LPT, it will not be good again. And this is again another of these like kind of mysterious features that somehow lambda CDM may happen that it works and so on. Well, this procedure order by order works always better and better. And no matter what happens, well, no matter what is the funny shape of the linear power spectrum, if you have some power on small scales or not, it will give you a sensible answer. Because we did some like proper treatment and understood really where the issue is, how to deal with it, and kept only terms that make sense. Okay? So that is a very nice calculation. I think one of the most beautiful calculations in perturbation theory, in fact, is the calculation of the BO peak. And so we got it right. And the same logic applies for bias tracers. Everything that I was saying here, in fact, applies to galaxies. It's just a simple shifts. There's nothing very complicated. And so the description of the BO peak can be made exact even for galaxy correlation function. And so when you want to go and measure, for example, the position of the peak, sometimes people fit the broadband by some polynomial, approximate this bump with some Gaussian, and phenomenologically this works. They can find, for example, where is the position of the peak before they do, for example, BO reconstruction. But there is no really need for that. We know how to calculate these things, and that is one very nice thing. We can really like take the formula, build the theoretical template, which will depend only on these kind of things, and some bias expansion, which is very good at 100 megaparsec, which is large scales, and fit the whole data points. And the first day I showed you some results from some very large and very high resolution simulations, which involve galaxies and satellites and all kinds of complications, and everything was perfect. The wiggles were fitted perfectly without any extra free parameters. So there are no free parameters here. It's all just simple gravitational dynamics where you have free fall. Nothing, no free parameters. Everything is fixed with the equivalence principle. And this is what makes this calculation very beautiful. Okay, I stop here.
Questions? Yes.
So I'm curious, is the Zildovich approach much more computationally costly, like much more, or just?
So it is not much more computationally costly. It is. I think that it becomes a bit costly if you go to higher order perturbation theories. For example, if you really want to do LPT at higher orders or higher loops, it's a bit more costly. And for instance, it is not immediately trivial how to apply all this technology of fast evaluation of the loop intervals that I talked about yesterday. So one advantage of SPT formulas is that we know how to evaluate them almost instantaneously.
Okay.
So there are all these tricks and technology. Now, for LPT, you can do something similar, but it is not as much developed. By the end of the day, you can really use both. There is really no like some strong reason why you want to prefer one or the other. I think that SPT is a bit more intuitive, maybe simpler to explain, more common, and maybe easier to deal with. But as I said, both perturbation theories are equivalent to each other.
But so the simulations that you talked about in the first day are all using the LPT, right?
No. The simulations are full n-body simulations.
Oh, the full, okay.
They don't. No. Here everything is like. So remember, I showed you some. Let's see if I can find it now. Yeah. So this is a full n-body simulation, and all these wiggles are right. I mean, the residuals they don't show any problem at a 0.1% level. So everything is perfectly fine.
Yeah, so in that expression, you said that if we naively take that lambda to infinity, then everything seems to work okay.
Yes.
But do you have any clue? Maybe I don't understand that part. Why this is so in lambda CDM?
I think that it's an accident. It just happens to be the case that exactly. So you see, if you don't include all these terms, you have to replace them by something. You replace them by the dynamical contribution of these terms and these terms. So shifts contribute only from larger scales. Then there are true dynamical contributions from all scales. When you combine them together, you get the right answer. Now, miraculously, if you just take into account the shifts and integrate to infinity, you get the same answer. But there is really no reason for that. If you have a slightly different cosmology, it will not work. It's just a coincidence.
Coincidence don't happen.
if I remember, there's a problem with LPT. There is stream crossing. If I don't.
Yes.
The same is present here in the EFT approach.
Well, usually, actually, the multiple streams or shell crossing is a problem in like I think I would say like more Eulerian perturbation theory, because here we really don't know what to do. Like in LPT, if you calculate the displacement field and you just move the particles, they can cross through each other. There is no problem there. So I think that there is even less of a problem, and some people are trying even to go beyond nonlinear scale, exploiting this fact. The real problem with LPT is that if you try to convert displacement fields where there is a shell crossing to densities, because then there is a Jacobian which becomes infinite. But this is only if you want to describe density field like when there is a but fundamentally, if you just think that you're moving particles and they cross, nothing bad happens, because simulations do that all the time. So in some other sense, if you basically if you somehow first move the particles, look at the field, smooth it, and calculate endpoint function, you may be better off than doing this theoretically, doing Jacobian and so on. But for example, in Eulerian perturbation theory, because as we said, we want to use some fluid description, there multiple streams are not allowed, and here we have to stay on large scales and do like a fluid approximation.
Okay, more questions? I just have one question. So you do have a free parameter here, epsilon. How do you fix epsilon?
Oh, Rogerio, you. So it is true. There is a free parameter, which is epsilon, and you choose it to be whatever, like 1, 1/2, 0.5, 0.8, 0.3. The thing is that epsilon dependence cancels. It cancels when you go to, like in other words, here there is some epsilon dependence, of course. But what am I doing? I'm like saying, oh, let me stop here. For some fixed K mode, let me stop here, okay? And then I introduce epsilon dependence. But when I go to the next order iteration of this logic, I will say, oh, let me actually stop here, only for the displacement part, but then I'm going to subtract a part of the displacement that I calculated perturbatively. I add it in the full one-loop calculation, and I go further and further and further. So I always push, so then there are contributions which cancels among each other, and I always push this epsilon dependence somehow to higher order in perturbation theory. So when I do, for example, the one-loop calculation, there will be no epsilon dependence in the one-loop part. It will become epsilon dependence in the two loops, and then if I include two-loop formula, it will be epsilon dependence in the three loops, and so on. So there is some small epsilon dependence, but it is not really important, yes. There is another parameter, by the way, which is that when I tell you act only on the wiggles, it means that you have to find some way to split the power spectrum into the wiggly and non-wiggly part, or alternatively to split the correlation function into smooth and the peak part, and that can be done. It is like always a bit of a choice, but again, like if I split them up, I massage them in a different way, I sum them up, the leading sensitivity to the splitting also cancels. But yes, there is a bit of a choice. And that's...
All right. So
let me say one more thing. Yes. There are other versions. I'm presenting this formula because it's very simple. There are other versions of the iris summation. You can look at the paper in the lecture notes of Leonardo Senatore. There are references to papers with Mattias Aldeaga where they do it without ever splitting into the wiggle, no wiggle, for instance. And that can be done. It is essentially starting from LPT, expanding all higher order terms, which are not displacements, and then treating displacements in full glory and so on. So somehow automatically, not somehow, but for a very good reason, automatically you get the iris sum power spectrum, and maybe I can even show some of these things tomorrow. You get the iris sum power spectrum, but you never had to split into wiggle, no wiggle, okay? But then maybe it's a bit less intuitive, and it's very technical. It's hard to read. I mean, it is very, very heavy. But once you have this intuition, I think it's good to go and take a look.
Okay, so let's thank Marko again. You know what he does? I think he just fits sigma for
Yes.
some simulations, right? That's what he does.
There is no reason, yes.
So the case, the shape, the formula, the dependence on k-square is the same. So it's just fitting sigma.
Yes. There is no reason. I mean, look.
There's no reason, right?
This 0.1%, when are you going to use more?
Yeah.
Still large, so yes. There's no reason. It's so sad. Nobody cared less about it.
But who uses sigma infinite? It's not my thing.
Well, yes, in the theoretical papers.
I understand that.
For example, in RPT, there is e to the minus sigma v squared.
Yes.
Multiplying the whole